Hello, this is Arthur Weglein from Houston, Texas. I want to begin by thanking Clement Kostov and Dr. Adele Eliman for and the organizers of the workshop for the opportunity of speaking here today. The topic of the workshop is multiples of the signal of noise. The topic of this particular presentation is multiple signal of noise. I'd like to thank our sponsors. There are two views of signal and noise. One is what we call the exclusive view, the dominant view, which is that primaries are signal and to be migrated and inverted, and multiples are a form of coherent noise to be removed. There's an inclusive view of events, which says that primaries and multiples are both to be considered signals and to be migrated and inverted. We hear a statement these days more and more often that we are no longer needing to remove multiples because we're going to be migrating both primaries and multiples. And so we, in this talk, want to examine both the exclusive and inclusive view and provide a perspective and some definition and clarity on this current topic of interest, and of interest defines the workshop that we're participating in. Since people who are claiming to be using multiples as signal are using it for migration, it's reasonable to start with what migration means, to provide some meaning to that term, so that when we say migrate primaries or migrate multiples, we're all understanding what that means. There are two components of wave theory methods to migrate seismic data. There's a wave propagation component, and there's an imaging condition. John Claerbout provided three imaging conditions for one-wave propagating waves. Back around 1971, he and his co-authors, students, provided three landmark contributions to seismic imaging. One was the exploding reflector model. The second is the time and space coincidence of up and downgoing waves. And the third is predicting a source and receiver experiment at a coincident source and receiver subsurface point and asking for time equals 0. These were the three imaging conditions of tremendous impact that John Claerbout brought to us. Imaging condition 3 defines wave equation migration. Imaging condition 3 has standalone properties and benefits in comparison with imaging condition 1 and 2. If you have a plane wave, normal incident on a single horizontal reflector, and you have a reflection that comes back, and you apply imaging condition 1, 2, or 3, you'll get the exact same result. As soon as you take the simplest horizontal reflector and non-offset data and apply imaging condition 2 or 3, you do not get the same result. And imaging condition 3 stands alone in terms of its definitiveness, in terms of whether you do or do not have a structure at a given point in the Earth. You bring a source and receiver down to some coincident point, you ask for small positive time, and you either do or do not get a non-zero value. If you get a 0 value, there is no structure there. If you get a non-zero value, you have structure there. That clarity is not shared by any other imaging condition. That's item 1. Since you predict experiment, source and receiver experiment at depth, you have the physics of what a source would do and a receiver would receive right above a reflector or right below a reflector. And that clarity in terms of amplitude is, again, only achievable with imaging condition 3. All current RTM methods, which address two-way waves, correspond to imaging condition 2. and do not correspond, nor do they provide the benefits of a coincident source and receiver experiment at depth at time equals 0. Equation 1 is a typical current RTM method that realizes imaging condition 2. R is some back-propagated reflection data for a given shot, and then S is a forward-propagating source field, and S prime is a complex conjugate. This is in the Fourier domain, and what you're doing here is doing a space-time coincidence of what is considered a down wave from the source and an up wave from the reflection data, and that's considered to be the image. This imaging condition is ad hoc. It has clear meaning in terms of 1D normal incidence. Once you move away from 1D normal incidence, the physics behind this is questionable at best. Here's an example from the Yang result with a perfect data, no noise, full aperture, perfect sampling with imaging condition 2 applied to imaging a single reflector with a single shot vector. The upper figure is the complete negative to positive offset response, and the figure at the bottom is an enlarged version of from the center to the right of the upper figure. And you can see the lack of any coherent output along that single reflector, where you should get a reflection coefficient that's the same value at every single point on the reflector. For the most complete data in the world and perfect data and a single horizontal reflector with known velocity above, that's what imaging condition 2 provides for a single shot vector. This is what imaging condition 3 provides for the same exact single shot vector. Slope migration is a realization for one-way waves of imaging condition 3. The coherence and interpretation of these two pictures, 11 and 12, the significance cannot be overstated. In this talk, we're going to adopt imaging condition 3, since it has the unique benefit of clarity and meaning. Not only do you know what the image means, you can extend it to not only get a reflection coefficient, but you can get an angle-dependent reflection coefficient from that imaging condition 3 by extending it, as people around Bob Stolt and his colleagues have over the years. And you can go further, as Bob Stolt has taken us, to going beyond specular, going to a point reflectivity for imaging and diffraction, only achievable through imaging condition 3. So in this talk, since we're interested in having the clearest, best defined method of migration for looking at what happens to primaries and multiples if you migrate them, it's natural that we would choose imaging condition 3. So imaging condition 3, as we said, has two ingredients. One is it predicts the source and receiver experiment at depth, and then it applies an imaging condition. Both the prediction of the source and receiver experiment and the imaging condition itself, both of those ingredients have evolved and progressed over time, as you would expect. But they owe their origin to John Claerbout's initial pioneering work. So one component of imaging condition 3, as we just said, is predict from actual measurements on the Earth's surface with sources, and each source having a set of receivers, and then you move the source from this collection of recorded data. How do you predict what a receiver would be at depth for the source still on top? And then how do you then, in step 2, predict both the receiver and the source at depth? 1828, George Green provided us the clear math physics, which was and remains the cornerstone in classic mathematical physics for how you predict a wave inside a volume, where you know the properties of the medium inside that volume in terms of surface measurements. This is not a controversial theory. On the right-hand side, what you have are the field and the normal derivative on a closed surface. That's what's inside this integral, this closed surface integral. This is the prediction of the wave, what you would measure if you had a phone inside the volume at a position R due to that same source on the surface. G0 is a Green's function, which is any Green's function, George Green taught us, that satisfies the properties inside the volume. It could be causal, anti-causal, or none of the above, as long as it satisfies the differential equation for properties inside the volume. This theorem holds. So we have an issue. In exploration seismology, we do not collect data around the volume. We have data on the top of a volume that we're trying to predict the wave inside of it. So we have data, if you like, or measured values of P in the normal derivative on the upper surface as upper, but not as lower. However, if in this region you have a wave that's moving up in this volume that you're trying to predict the wave, if that wave that you're trying to predict is upgoing everywhere in that volume, then you can show that choosing an anti-causal Green's function, among the infinite choices of Green's function, pick the anti-causal Green's function, then with that choice, the contribution from the upper surface will predict P, and there is no contribution from the lower. That realization then allows you with this anti-causal Green's function, which we in addition arranged to vanish on the upper surface, not to need the normal derivative. That's what the superscript D represents. This is a double sum. A sum over sources, a sum over shots. The sum over geophones, receivers, brings the receiver down. I shouldn't say brings the receiver down. Predicts what the receiver will be in the volume. And the sum over shot predicts then what the shot would be in the earth for a position of the shot in the earth and a receiver in the earth. Then we go to John Claerbout and use an imaging condition and say, from those two anywhere predicted source and receiver in that volume, make them coincident and ask for T equals 0. The result of that is pre-stack slope migration. Okay, now let's say we go to two-way waves. Now we're in a region where waves are moving up and down. For two-way propagation, the need to get rid of the lower surface is more complicated, and you have to pick a Green's function that satisfies the properties in the medium, which vanishes on the lower surface along with its normal derivative. So the Green's function and its normal derivative both vanish on the lower surface, and that will allow you, from measurements of only the wave field on the upper surface, to predict a two-way wave experiment, to predict a source and receiver experiment inside a volume where the waves are moving in two directions. That's the result of that. You get a sum over geophone, a sum over shot, with complicated weights. This work was done very recently, 2011. To my surprise, we were the first to publish this kind of thing. This gives you, and here are the references. These are referenced in the Journal of Seismic Exploration. Okay, so this gives you how to predict the wave, how to predict the experiment for Claerbout imaging condition 3, when the waves in that medium are moving up and down, and you want to predict what a source and receiver would record inside that volume. That's what this does. Okay, so you have two methods here for RTM. You have the equation 5, which is the current industry standard, which involves a sum over receivers in some way to bring the wave field down for a given shot. And then there's a sum over sources. And you have here a sum over receivers and sources. These two, equation 5, which is Claerbout imaging condition 2 for two-way waves, and 6, which is Claerbout imaging condition 3 for two-way waves, could not be more different. Why they sum over sources in equation 5 is because of that picture you saw from Weglein. That picture does not look like a single consistent output of reflector amplitude along that single reflector with perfect data. So they sum over sources as if the data had noise. The data doesn't have noise. In 5, the algorithm has noise. The algorithm is challenged, and for that reason they're summing, hoping to somehow sum so something consistent will occur at every point under the particular source. The difference in 6 is when you sum over receivers, first of all, for a single horizontal reflector, you get a consistent result. That's what Weglein showed 3-4 slides back. If it isn't horizontal, what the sum over receivers does in general is predict the receiver inside the volume for the source still on the surface. And it does that exactly. What the sum over sources does is not in any way to fix what the sum over receivers has done. It brings the source down. So each is doing something correct, and the sum over sources is not there to correct some kind of challenged sum over receivers. So you need to employ that equation 6 if you're serious about predicting an image that you can interpret, that you can have confidence in the math physics of what the image means and its ability to be extended to angle dependence. In a two-way wave situation, 6 is what you need if you're serious about that. And we're serious about it because in the particular discussion here today, we're looking at what happens to primaries and multiples when you migrate them. So when you migrate them, you have to migrate them using equation 6. So what we're going to do, now that we have this migration machinery, which allows us to predict a source and receiver experiment inside an Earth where waves can be moving up and down, what kind of situation do you need where waves are moving up and down? As soon as you move below a single reflector, you're in a volume where waves are moving up and down. So if you're serious about migrating through a single reflector, the mechanism and technology and capability that we're describing here today is recommended. What people are doing with current RTM is they're struggling. They have an ad hoc method, they do something through that reflector, and then they have an ad hoc method to try to fix it, not knowing that the method itself is challenged to begin with. Okay, so what we're going to do is, now that we know which migration method we're going to choose, is we're going to put primaries, free surface multiples, and internal multiples into the data and migrate them with imaging condition 3. And then see, as this experiment is predicted at different depths, and then you apply the imaging condition that the source and receiver become coincident at time equals 0, that you will see which events in the surface data contribute to the experiment at different depths, and most importantly, which events in the original surface data contribute to the image at different depths. So here's a primary. Okay, so what that movie represents is what that math in that equation with all those G0 DNs are predicting. This just shows you how what the source and receiver look like. So you can see that this original primary is being transformed to different primary in the data that's being predicted for that experiment at depth. And then when you're right above the first reflector, and you look at all time, and then you ask for t equals 0, you get the reflection coefficient there. And then when you're right below, and you ask for t equals 0 for that predicted experiment, you get minus R1. Here we have a primary and a free surface multiple. And here's the movie as following the events as the experiment goes down. So when you see when the source and receiver is right above the first reflector, right here, the primary, which is originally from here, is now this. The free surface multiple, which is originally like that, is now this. When you ask for t equals 0, the new primary, which is at depth, only came from the original primary. The free surface multiple that came from the original free surface multiple here, when it's now in this new experiment, its contribution comes in later than t equals 0, hence does not contribute to the image. Yes, that's the point. That's the whole point. And that continues. Here we have two primaries and an internal multiple. And you can see the experiment, you can see what happens at each depth, and you can see which events, because this movie is color-coded, so you can see which events contribute to the experiment at depth and then to the image at depth. Okay. So this just shows you the math from a paper by Fontaine and myself that appeared this month with the explicit, this is the total wave field at depth between the first and second reflector. This is the reflection data. And then when you ask for t equals 0, you sure enough get right below the first reflector minus R1, and right above the second reflector R2. And you can see from the math, although it's not as transparent as these movies, that only the primary, the original primaries contribute to the primary that is above or below each of those image reflectors. So, the bottom line is, if you have an accurate, discontinuous velocity and density model, then we have unambiguously showed with the most math, physics-based of imaging conditions, Claerbout imaging 3, that primaries in your reflection data and free surface multiples and internal multiples all will contribute to the predicted source and receiver experiment at depth. They will predict other events in that new experiment. Once you ask for t equals 0 for that coincident source and receiver, then the contribution only from primaries in the original data contribute to the image, meaning multiples play no role If you had primaries and no multiples, you get the same image. If you had multiples and no primaries, you'd get no image. So if for a discontinuous accurate velocity and density model, multiples provide no help, no harm. In practice, we have primaries that are migrated with a smooth velocity because we can't find a discontinuous velocity accurately enough. For a continuous velocity, primaries can be well located. Every single free surface and internal multiple will give you a false event. And that's the reason multiples were needed to be removed and continue to be needed to be removed. So what's the recent work with imaging with multiples? No one's imaging with multiples. No one is imaging with multiples with anything that Claerbout imaging condition 3 would recognize. What is happening, imaging with multiples, is actually using a recorded multiple, the black line, and a recorded sub-event, the red line, a longer offset sub-event of that multiple, to predict a shorter offset primary that was not recorded, the blue. So there's this, we'll take the multiples back, we'll take the primary forward, and sort of that back and forward produces something like the blue primary. That's the idea. There's a problem there in that how are you going to predict a multiple if you don't have the blue and the red? If you don't have the blue and the red, you can't predict the black as a multiple. So what people do in practice is they put the whole data in. The data contains primaries and multiples, and certainly the you don't have to predict them, you just put the data in. And then the primaries on the other side that are being forward propagated, when they interact with a multiple of a certain order, will produce this blue primary sub-event. But every time one of those primaries interacts with a primary, it will produce an artifact. So here's an example of that kind of procedure that PGS is applying. Here's the data with the original primaries. Here's the data from the original primaries plus predicted primaries, where a primary was extracted from a multiple and a sub-event primary from within the multiple. And you can see the image improved, that shallow in particular. So there's value in that. So what we advocate is you need to have as wide and complete a coverage as primaries as possible. Collect them, interpolate them, use a multiple to drag out a primary, all good things, all to be supported and encouraged. Once you finish having as complete a set of primaries as you can get, and now you have primaries and free surface and internal multiples, then your job is to remove the multiples, because if you don't, you better have an accurate discontinuous velocity. Okay. So that both the arranging for more complete set of primaries and the removal of multiples, neither of those are closed subjects. There's been progress, but there are more things to do. So a multiple can be useful. A multiple can be useful just like money is useful. If you don't have money, you don't have a primary. You don't have a boat, you don't have a primary in the ocean. You don't have a cable, you don't have a primary in the ocean. All those things are useful and necessary. Okay? So a multiple can be useful to get primaries, but once you have primaries, it's primaries that you need to be using in your imaging. And if that's what you define signal as, what you use in terms of events that are used to locate and invert for subsurface properties, then primaries are signal and multiples remain noise. I want to again thank the organizers and Clement Kostov and Dr. Adel El-Imam for the opportunity to speak here today. We're coming up to Thanksgiving in the United States. I have much to be thankful for. including the opportunity to present. And I want to acknowledge all the people whose conversations aided our understanding